Hello, and welcome to my presentation about gaze-dependent simulation of light perception in virtual reality. My name is Laura Luidold, I'm from TU Wien, and I was working with Michael Wiemer and Katharina Grösel. The displayable range of low dynamic range monitors is significantly less than the human perceivable range. The brightness of an image needs to be compressed to properly display high dynamic range images on LDR monitors. This compression is commonly done using tone mappers. However, these algorithms are focused on 2D displays, where the perception is inherently different than natural human vision. Glare or scotopic vision and other specific light effects are not triggered in the eye on common monitors. For convincingly realistic VR scenes, immersion is a significant factor. Therefore, we need to simulate what can't be seen on LDR displays. Algorithms approximating the human perception are necessary for realistic simulations. A medical basis can help to understand and simulate such visual effects. The gaze direction and the pupil size play an important role in these effects as well. Finally, such algorithms can be used for more accurate simulation of eye diseases, more realistic architectural lighting design, as well as VR games. We propose a post-processing workflow that allows accurate simulation of human light perception in virtual reality and augmented reality. Our medically based perceptual effects are able to run in real time following an optometrist's advice. We include eye tracking to measure the light incidence into the human eye, and our algorithms account for the user's gaze point. For evaluation, we conducted a pilot user study that compared a real-world low-light scene to our simulation in VR. The following 4 methods are included in our application. First, we adjust the brightness of the scene over time to simulate the adaptation of rods and cones. Rods and cones are the photoreceptors in our eyes, which process the incoming light. Here on the left side, you can see the non-adapted original scene, and on the right side, the fully adapted scene after approximately 3 seconds. Secondly, we simulate the glaring effect we perceive when looking at bright light sources. This phenomenon is caused by the scattering of light inside the human eye. Here we see a comparison of a standard bloom to our perceptual glare. Additionally, the loss of visual acuity in low light scenes is included in our application. In darker environments, we are not able to make out many details due to the rods not being present in the fovea. This is a rather subtle effect, but on this close-up you can see the difference between the visual acuity reduction effect turned off and on. Last, we add a bluish color shift as naturally perceived in low light scenes. This effect appears due to the rods being more sensitive to longer wavelengths of light than the cones during daylight. Here we see the difference between the scene's original colors and the shifted colors. In the following, I will talk about the details about those 4 effects. For the temporal eye adaptation, we first calculate a target luminance for every frame, which is weighted by the gaze direction. Then we use an exponential function that takes the target luminance, last frame's luminance, as well as the adaptation times of rods and cones into account. This gives us a temporally filtered luminance value for our current frame, which is then multiplied with the linear RGB values of the frame. For the glare, we will first have a look at why this phenomenon actually occurs. On the slides, you can see the side view of a human eye. In our simulation, we simplified the lens at the front of the eye as a 2D plane that basically looks like this. The white region signifies that light is able to pass through. This means it is the aperture of the eye. The size of this 2D pupil is adapted according to the measured real-time value from our eye tracker. Now, a single wavelength light ray passes through the lens and hits the retina at the fovea, which is the center. Now, imagine another 2D plane that is located at the back of our eyes, which represents the retina. Our green light ray hitting the retina plane would look something like this. However, it's not that simple. The human eye, specifically the cornea and the lens, contains small irregularities or particles that scatter the incoming light. These particles are here displayed as dots. There are many thousands located in the lens, and they are the main influence in creating the glare. When our light ray hits one of those particles, It scatters and we receive a pattern at the retina like this. Due to the wave characteristic of light, we can calculate the scattering of rays on the particles as the diffraction of waves on an obstacle. After Ritschl et al., we apply the Huygens-Fresnel principle to calculate the diffraction pattern. We use a pre-calculated random dot pattern as well as the real-time pupil size from our eye tracker. The amount of particles can be individually adjusted. We used 1000 particles in our simulation. The shown diffraction pattern is a so-called monochromatic point spread function. It describes the way the scattering of a single wavelength light appears. However, usually lights consist of multiple rays of different wavelengths, which is why we need to combine multiple scaled copies of this monochromatic PSF over the full human perceivable spectrum. This combination gives us our glare kernel, the spectral PSF, when assuming equal energy light. Finally, we need to apply our kernel to our simulated image. This is done by a convolution of the image and the kernel. However, transforming both VR views for the right and the left eye to frequency space for every frame is very costly and not feasible in VR. Therefore, we only apply the kernel to a 1024 x 1024 window centered on the gaze points. Afterwards, we blend the convolved window with the original image. This results in a more accurate simulation of glare influence on the human eye due to the lower influence at the periphery. Additionally, we achieve a significant speedup. For the visual acuity reduction, we transformed our image to the LAB color space because it is perceptually linear. We blur only the lightness value L with a Gaussian filter. The kernel of this filter uses a sigma depending on the current lightness of every pixel. We introduce a new, simpler formula for this. It is based on medical data that describes the maximum perceivable visual acuity at the lightness L. Therefore, our approach blurs dark areas stronger than areas that are in the light. After the tone mapping, we apply a lavender color shift according to the sensitivity of the rods. This is done depending on the brightness of every individual pixel. So we simulate the bluish-purple tint that we perceive in low light scenes, especially during scotopic vision. For evaluation, we conducted a user study with 5 participants, with normal or corrected to normal vision. The participants were asked to compare the real-world perception to our simulation and graded on a Likert scale from 1 to 7. The white bars show the average ratings and the smaller black bars signify the 25 and 75 percentile. Generally, our application was well received, where only the appearance of the glare was rated less than 5. Overall, we conclude that visual perception is different for every person, and to create a universal perceptual realistic experience, we need individual adaptation for the user. To conclude, we presented a real-time VR and AR post-processing workflow that can be added to any renderer. We use eye tracking to generate more realistic simulations, while our implementations are based on medical research. Finally, we held a pilot user study which showed that our 4 implemented effects were well received, namely the temporal eye adaptation, a perceptual glare, visual acuity reduction, and scotopic color vision. Our glare implementation is already in use in a cataract simulation. If you're interested into the details, refer to the paper Cataract Simulating Cataracts in Augmented Reality, which is also presented at ISMA this year. For future work, further medical specifications could be included, such as lens deformations or a more detailed glare kernel. Additional effects, such as after images or noise in scotopic vision, also impact our visual perception and are not accounted for yet in our application. Additionally, further user studies using an HDR display for comparison or evaluating our implementation in AR should be held. This concludes my presentation. Thank you for your virtual attention, and if you have any questions, feel free to ask them in the live Q&A. Thank you.